Hello, good morning, good evening, good afternoon, everybody, wherever it might be. It is my great honor and pleasure to welcome MASOUD KHALKHALI. We have known each other for so many decades. It's a pleasure to have you on board of a seminar. And MASOUD will tell us about something, quite exotic in non-commutative geometry. Namely, it will be the Berkovich projective line and its non-commutative geometry. MASOUD, it's all yours. Take it away.
Oh, thank you very much, Piotr. Thanks for I should thank all organizers for the kind invitation. It's a real great pleasure to be here and to talk in your seminar again. Okay, so as you can see, this is a joint work with Damian Tajdin from McGill University. Um, it's published, of course, the journal, the article is also available. The latest version is available on the archive. And I believe Journal of Fractal Geometry, published by European Math Society, I think it's freely available in many universities. So, so where to start? Okay, so I will gradually introduce some of the main characters. More or less, there are two kind of main characters in the game. One is the field of p-adic complex numbers, which we denote by CP. And then I will spend some time explaining some applications of CP and analysis on CP. And then I will try to convince you why CP is not good enough, and we have to move on to something much more exotic and perhaps abstract, which will solve some of the problems that CP suffers from. Okay, so what is CP, the field of p-adic complex numbers? The process is very similar to some extent to the way we get complex numbers C from rational numbers. So rational numbers is not topologically or metrically complete. You have absolute value on usual absolute value on rational numbers. You complete it, you get R, and then you complete R algebraically in the sense that you close it up algebraically, because you notice immediately that R is not algebraically closed. When you close R algebraically, you get the field of complex numbers C, which is, we know, and it's a fascinating object. Of course, already there a miracle happens, namely, if you add just one root of second degree equation, then all equations can be solved all of a sudden. This is the fundamental theorem of algebra. But nothing like that happens with p-adic numbers and their closure. So where to start? So instead of starting at infinity, which would be what I was talking about, we start at finite prime p, and we define a valuation, absolute value or valuation on rational numbers. Basically, this picks up Vp of x, the p valuation of a rational number picks up the exponent of p in x. So if x is an integer, is this the highest power of p that divides x. If it is the quotient of two relatively prime integers, you just subtract them. So using that, you can define a p-adic, the p-adic absolute value, which is defined as xp. Absolute value is p to the minus vp of x, and you just define absolute value, p-adic value of 0 to be 0. So this is a metric, but its metric property, the triangle inequality, a much stronger version of triangle inequality holds. Namely, it satisfies the ultrametric property that x plus y, the length of x plus y is less than or equal to not the sum of, but actually less than max of x, the absolute value of x and absolute value of y. So this is the ultrametric or non-Archimedean metric property. I should say these two things, the usual absolute value and this one, are essentially all the absolute values, reasonable absolute values you can define on Q. I mean, you can modify this by changing P to any powers, but there's just a rescaling. Essentially, there's a term of Ostrovsky that tells you that these are, yeah, the usual absolute value we learn in high school, and this one. These are all the possible good absolute values on rational numbers. Okay, and then we play the same game. You notice, so you define QP to be the completion of Q under the p-adic metric. And then what you can do, to get CP, you do the algebraic closure of QP. QP is not algebraically closed, but in this case, you have to add infinitely many new roots to QP to close it algebraically. And as a result of that, the distance between QP bar and QP is huge. It's an infinite extension. So this is not topologically complete anymore. So you have to complete it. So you complete it, and then you get this field of p-adic complex numbers CP. So yeah, but the magic here, the miracle here is that this completion now is algebraically closed. So the process stops this time after 3 times. So this is also a kind of miracle on its own. So it happens. So
Sorry, Masoud, if I might ask you, you have
yeah,
a bar, you have a hat. So
yes,
which signifies what? One is
yeah.
algebraic completion, one is topological or metric completion. So
Yeah. Good question. Yeah, bar is algebraic completion and
okay,
hat is topological completion. Yeah.
okay,
And remember, QP is already Q hat. So with respect to the p-adic metric.
okay.
So, okay,
So it
well,
becomes incomplete only after you algebraically complete it. It becomes metrically incomplete after you algebraically complete it.
you mean, are you talking about QP?
Yes.
After we algebraically complete it, it's not complete topologically. You have
Yeah,
to
yeah. That's what
complete
I
it.
was saying. Yes,
But
yeah.
then it is that's the end of the process. You get something which is both algebraically complete and topologically complete,
Yeah.
and that's CP. So the story is kind of summarized here in these two things. So at p equal to infinity, we have the usual story. This q infinity is r, is real numbers. It's notation for now. And for finite p, we have this series of extensions q to qp, qp bar, and cp. So we get this field of p-adic complex numbers. And okay, so now the question is, what's it good for and why it was introduced? Well, let me first tell you some of the problems with this. I mean, the topology of these p-adic numbers, like any non-Archimedean topology based question.
No, sorry, I was just clearing my
Yeah,
throat. So.
sure. Like any non-Archimedean topology is very, very strange and it's hard to conceive, visualize. So, I mean, QP and CP, they're both totally disconnected. So they are like Cantor sets. They are zero-dimensional essentially, but they are not discrete. They have topology. Every point of a ball is a center. So if you take any point in a ball, it's the center of the ball. All triangles are isosceles. If you take any triangle, two of the sides are actually equal. Open balls are closed and closed balls are open.
Mhm.
Another strange property is that if two balls meet, then either one of them is contained in the other. If they
Mhm.
ever intersect, either this one is, yeah, left is inside the right, or right one is inside the left one. So there is no kind of intersection, incomplete intersection.
May I have a question?
Well, yes, go ahead.
Yes, yes.
So you mentioned that it is like a counter set. So is it homeomorphic to a counter set, this CP?
No, CP, I believe no, it's not homeomorphic to counter set at all. No, that's not.
Mhm.
Topologically, it's not. But QP is very much like it is closer, but CP is much wilder. Yeah, that's
Okay.
what I think. Yeah. Okay.
Okay, thank you.
Yeah,
So
thank you.
Masoud, because there is a theorem, right, that characterizes a counter set. It's the unique,
Yeah,
totally disconnected, perfect.
Perfect.
yeah,
So
Yeah.
one of these
yeah.
conditions maybe is not satisfied in this case.
That's right. That's right.
Zero
Yeah.
dimensional, I think also, and metrizable, compact metrizable. Yes.
Well, these are
Yeah,
totally
these are
disconnected.
metrizable.
So,
Yeah,
yeah.
yeah, yeah.
Mhm.
And also
I
zero
mean,
dimensional because they're totally
yeah,
disconnected.
yeah. I mean,
So
but yeah, yeah. Go
So
ahead.
ultrametric spaces, they have a lot of properties of counter set. Usually I think that only perfect is the one missing. Okay,
Yeah.
one can check. There is this
Okay, so
theorem.
there are some isolated points, yes, in the CP.
In the CP, there are some isolated points. I'm not sure. I have difficulty conceiving CP.
Since this
I'll try to show you some pictures later on.
there
But
is negation of being a perfect space means that there are some
okay.
isolated
Yeah,
points.
yeah. Okay. So yeah, it could be. Yeah, there might be.
Mhm.
Yeah, yeah, yeah. Right. By the way, I mean, as a field, CP is isomorphic algebraically to C, to the field of complex numbers.
Oh,
This is another surprise. Yeah, but this
oh.
isomorphism, I mean, it follows from general field theory result, but this isomorphism is totally useless because it's not continuous. So
Ah.
it's hardly used, but it is not absolutely useless. I mean, I said totally useless. Okay, I should have said it's mostly useless, but it's not totally useless. It's not absolutely useless. There are some applications of these non-canonical isomorphisms in
But sorry,
algebra.
but how about being compact or locally compact
Oh yeah,
regarding
it's
this
not.
CP?
It's not. Yeah, yeah. So CP is not locally compact. Yeah,
Ah, okay. So
it's not.
maybe this
Yeah,
is the reason for not being
yeah,
isomorphic
it's not.
counter set.
Yes,
So
yes. So
probably
yeah,
it will be
yeah,
still
yeah,
true
yeah,
that there are no isolated points. It still could be. So yes.
yeah.
Okay.
Okay,
Thank you.
so let me move on. So here's I'm comparing QP with CP. So in terms of completeness, both are complete topologically. QP, as we know, is locally compact because you can do a hard measure Fourier analysis on QP, but on CP there's no. Uh, it's not locally compact. Is not
But
separable.
wait, Masoud, but it's a bit funny because Q itself is not locally compact, right?
But QP is, yeah,
But QP is, so it's funny.
yeah.
It's
QP is.
by taking P, it becomes
For,
a more regular
I mean,
space.
for example, R is locally compact. I mean,
Yeah.
Yeah, but Q is not.
so
Okay.
yeah, but Q is not. Okay, good. Yeah. So the value groups are different. So the value group, the set of values of valuations in QP is P to the Z, as we discussed, but in CP, these valuations extend and it's P to the Q. So it means that there are many, many different scales of smallness and bigness being close to the zero and away in CP, because the roots of P also enters the game. But in QP is only P to some powers. In terms of totally disconnect, both are totally disconnected, and the unit ball in QP is compact. I'll show you what unit ball in QP is basically ZP, but in CP is not compact. So that's so here is just I mean just so basically the lesson is that basically to think about p-adic numbers, the best way is to think of them as trees. That's a good picture. So every kind of system of branches all the way up to the base here forms one p-adic number. For example, the leftmost is just zero. And then, so these are p-adic integers. So if you want to take QP, you have to allow negative powers. Only finite negative powers is okay. That's it. You get QP. But CP, I cannot define it like that. I just is a bit more complicated. Okay, so that's the thing. Now the question is why these guys are kind of interesting. I want to take a little more general point of view. So instead of getting right away into the paper, I want to give you a little kind of sort of stories around these things. First of all, QP, analysis on QP was already used by Bernard Work in 1960 when he proved the first conjecture of series of wave conjectures. So this was really a shocking result. I will explain a little bit, just a bit of that very soon, but this was quite a fascinating application of analysis over p-adic numbers. Of course, it was used before. Even people say, if you read these things, people say, for good reasons, with good reasons, that even Kummer already was using p-adic numbers in his number theory studies. Kummer congruences for Bernoulli numbers, the denominators of Bernoulli numbers, I believe. It's very much tells something about p-adic numbers. Formally, p-adic numbers were introduced by Kurt Hensel in 1899. He has a book on number theory that right away starts with p-adic numbers. Okay, now in physics, there is a spin glass theory, which is amazingly beautiful theory, uses p-adic numbers in a very serious way. And of course, there is more kind of conjectural, but still mathematically fascinating p-adic ADS CFT correspondence and holography. I will tell you a little bit about those as well. So let's go back to work of work. Well, as you know, of course, wave conjecture is about counting the number of solutions that satisfy equations over finite fields, basically. Number of points in varieties over finite fields, say FQ. So if you let Fm and M to be the number of points in a variety over FQ, then you can look at solutions over FQ2, FQ3, the towers of field extensions that you have, and you have these numbers. And wave conjecture, basically, the first one asks you, or actually conjectures, postulates a very precise relation, more or less, between these numbers and sub m, the sequence of numbers, which is really amazing when you think about it, that why there should be such pattern among these numbers. So the way that it's economically formulated is you form this. This should be called Hasse-Weil zeta function. Perhaps maybe even Artin had a hand in writing this sort of. This is essentially a kind of generating function, but it's written deliberately in this form because in this form it behaves much better with respect to Cartesian product of varieties and other type of properties you want. So this is the essentially, we would say, a kind of generating function for these numbers and m. So it's called it zeta function, Weil zeta function of variety v. T is just a parameter, formal parameter.
And can you tell me one more time what is this m number?
And it's very simple. You just take a system of equations, whatever you want, with coefficients in FQ, okay?
Yeah.
With coefficient FQ. So you have system of Diophantine equations, bunch of Diophantine equations with coefficients in FQ, and then you count the number of solutions if you allow yourself solutions over FQM. Because FQ is inside FQM, so you can count number of solutions. You allow more and more room. But each of these fields, FQMs, are finite, so these NMs, these numbers are finite numbers. And the thing is, there is a pattern in these numbers. There's a hidden symmetry in these numbers, which is the content of the first wave conjecture. And actually, the way it is written, one way of writing it, I'll write another way soon, but one way of writing is that this number, this zeta function is actually a rational function. It's a power series, all right? It's a power series. In fact, with integer coefficients that you can prove with a little bit of work. It's not obvious, but you can prove it. But this power series with integer coefficients is actually a rational function. Now, what does this mean? It means.
Sorry, Masoud, one more stupid question.
Yeah.
When you look at this NM, is it obvious or true that this number is unbounded when you vary m to infinity?
No, it's not obvious to me. It could be that solutions do not increase, but we'll see that they will increase. Yeah, it's not.
Okay.
It's
not obvious, but it's true. Okay.
Yeah. It's not obvious to me at least, but I mean, we'll see that they will increase. Yeah.
Okay. Thank you.
Okay. So now, if this rationality statement is true, you can write this zeta function in this form. You decompose into its roots, the numerator and denominator like that. And then immediately from this expression, it follows that Nm is of the form sum alpha I to the m minus sum beta j to the m, where alpha I, beta j are essentially inverse roots of numerator and denominators. And then it shows that these numbers are completely determined by just the first few of them. So if you know just the first few, depending on the powers of these things, these polynomials of these numbers Nm, then you know all of them. And so this is the pattern on these numbers. There are complex numbers alpha I and beta j such that Nm is of this form necessarily. So this is the first Bay conjecture. There are 2, 3 others which I won't discuss. So Work's idea was to use p-adic basically analysis. I wouldn't say complex analysis, but let me just make a digression here maybe to tell you that if you have a function, for example, from CP to CP, you can define it easily to be analytic on a disk if it's convergent like that. The series like complex analysis. Now, if you try to define something like p-adic exponentials, you notice that this exponential function has finite radius of convergence, and the radius of convergence depends on p. So it's not infinite radius of convergence in the case like in the complex case. So for p equal to infinity, it has infinite radius of convergence. For finite p, it has. So this is the beginning of a lot of differences between doing analysis on QP and Q and R. So now the idea that Work actually used was an old theorem due to Emil Borel, not Armand Borel. Emil Borel. Actually, the theorem goes back to late 19th century, if not just, I believe you would say around 1900 at most. The theorem is a fascinating theorem of complex analysis that if you have a meromorphic function which has a power series expansion with integer coefficients, and if it has radius of convergence bigger than 1, then that meromorphic function is a rational function. So you see this integrality of coefficients and the bigness of the radius of convergence forces rationality. So Work, could not directly use this result because there's quite a huge distance between this result and this zeta function. So he developed a p-adic functional analysis, determinants, Fredholm theory, compactness, a lot of stuff, a lot of functional analysis over p-adic numbers. Bernard Work developed, and then he proved the first Bay conjecture. So it is attributed to Grothendieck that once he saw the result of Work, he has said that Work proved the theorem, but the proof did not explain why the theorem should be true.
Yes, nice.
Perhaps it's a bit unfair, but because Grothendieck had this alternative idea that everything should come from, for this wave conjecture, should come from Lefschetz's fixed point formula, but for the right cohomology theory, which but of course, the importance of Work's result is that it eventually merged with Grothendieck's cohomological approach, étale cohomology, and this is much more became modernized, and the two things actually are very much kind of going hand in hand at that time. Yeah, so yeah, I mean, if you have access to Grothendieck's correspondence, the section when they discuss this Work's result, I read it some time ago. It must be very interesting to read. So, okay, question? Sorry. Okay, so now the thing about the work of Parisi about these spin glasses. So spin glasses are a special kind of material that are they are not like Ising model because they're far more complicated, and they show properties that they're glassy in the sense that that they can behave sometimes like a magnet, sometimes like a not magnet, and it's the properties are the model is very much like Ising model, except that the coupling constants are random variables. So this model is basically at the root of neural networks, the Hopfield model, and then Sherrington-Kirkpatrick model, which was a bit more generalization of that. So these models were around, but they couldn't work with them because they could not solve them even approximately. I believe, and it was eventually. Yeah.
May I have a stupid and embarrassing question? When you
Yeah.
are saying about the model, what exactly do we mean by that? A specification of a Hilbert space and Hamiltonian and something
Yes.
more, or?
Yes, exactly. Even, yeah, exactly. I mean, there is a Hamiltonian, but Hamiltonian is a random operator in this case. Yeah,
Run. Ah.
random operator. So it's a random variable, which is a random operator. And so you want to study the average, the expectation values, the fluctuations, and all these things about magnetizations, about susceptibility, and all properties of physical system. You wanna say something about them.
Okay, so maybe using slightly more, I don't know, maybe more mathematical language instead of a language coming from physics, it would mean
Yeah.
that we have a measure on a space of all possible Hamiltonians, yes?
Yes.
It would be very problematic in infinite dimensions, so I suppose that here everything is finite dimensional. Is it true?
No. Okay, so there are two problems. I mean, you see, random walk, for example, is already you're dealing with an infinite dimensional space, and that can be defined. I mean, the Wiener measure, for example, it
Uh-huh.
exists. So that's okay. I mean, Brownian motion, for example,
Okay.
now
Sure.
people are doing random surface theory, which is also worked out mathematically, is rigorous. Although, I mean, three-dimensional fields, random fields, nobody has any real idea. And this is also closely related to quantum field theory problems.
Mhm.
But that's one thing. But then there is also this thermodynamic limit. Maybe you're mentioning that the thermodynamic limit you want to yeah, because you do the lattice approximation and then you want to take the limit. That's okay. I mean, that you can, after you understand the finite thing, the taking thermodynamic limit at the level of, for physicists, is okay. Of course, mathematically, it's quite challenging still. Yeah.
Okay, but the basic setting is the measure on the set of n by n Hermitian matrices with maybe some condition, additional
Yeah.
condition, and
If you
then we
want.
are, and then
Yeah.
n goes to infinity, yes?
Yeah. If you want, yeah, that's some kind of picture you want to have. But these models are very much like actually a part of everyday life. I mean, so So let me show you the picture. This is what I made using AI. I asked my AI. I put him to task. I thought, okay, draw this, and it produced this for me. I could have never done this myself, of course, but produce. So you see, this is what you were talking about. This is the energy landscape of these models. Usually in you see in Ising models, there is a unique kind of minimum, which is the kind of equilibrium state. There's a unique equilibrium. But here they don't have a unique, they have many almost equilibrium or sort of equilibrium state. They call it metastable state. By the way, they think people, very serious people actually think that that's the reason that we can memorize many things. Because everything you memorize is more or less a result of a kind of a stable point or almost a stable point in a kind of your I don't know, brain field or something. Because there is this neural network model for the way, I mean, this Hopfield model, how the brain works, right? So existence of many equilibria is actually related to the fact that we can memorize, we can remember many things. Otherwise, we would be able to remember one thing only. That would be the unique equilibrium. Okay, but what Parisi realized is that there is actually a kind of ultrametric behavior among these minima. So there are infinite number of, there are a lot of minima, but there is a pattern in this minima which was discovered by Parisi. So he defined a metric, and yeah, this is quite a big story. I don't want to get into it. I want to tell you that p-adic numbers actually are quite how to say are really part of our life. Maybe we should not think of them as very mathematical. They're actually like they're in everyday life. Well, trees are part of our lives, and p-adic numbers are very much like trees. Okay. Anyhow, so there is another application that I want to recall, but pass quickly. So there is a work by Gupser, I believe, started by Gupser, and then Marcoli, Saberi, and some other people collaborated together. There are several papers on this. So they were able to verify or to work out, I don't know how to phrase it, this ADS-CFT. Basically, this is the program in physics initiated by string theorists that gravity in the bulk corresponds to conformal field theory on the boundary of your space-time. And because we understand conformal field theory much better, so that's the kind of avenue to formulating or to understanding or defining or grasping quantum gravity as conformal field theory, basically, because of this correspondence. This is the boundary and bulk correspondence. So in their case, they look at p-adic numbers, SL2QP, and then this discrete subgroup SL2ZP, the p-adic numbers. And the quotient is something that I will show its picture, is the Brouhatitz tree. This is the exact analog of the quotient of SL2R by SO2, which is the Poincare upper half plane H2. You see, SL2R acts on the upper half plane by Mobius transformations, and the isotopy or isotropic group of one point, for example, I, is SO2, and if it's acting transitively, otherwise, the quotient is upper half plane. And there's a very similar picture in the p-adic world. SL2QP by SL2ZP is this Poincare upper half plane in the world of p-adic numbers, which are these Brouhatitz trees. But we can actually describe these Brouhatitz trees very effectively. This was the work of Brouhatitz. Burhatitz, which is in this case, you can see again, I used the AI to draw this with all the features I wanted. So I think what you see there is very much like basically the Burhatitz tree of SL2Q2. These are really buildings. These are very simple types of buildings in the theory of buildings. So yeah, so this
Sorry,
is
Masoud, I believe you have a typo.
sorry,
Because you have a typo. I think here it's an S.
which one?
Here.
Okay, I don't see it, but that's okay. I'm sorry. Yeah,
In
I'm
the
sorry
Well,
for
I
the
marked it in
title.
red. You wrote Tits with a Z.
Oh,
In the title of the slide.
In the
oh, your
title of the
title. Oh,
slide.
yeah. I'm sorry. I'm sorry. Yeah. Yeah, there is a Tietze, but that's a different
No,
mathematician
no.
and it's a different name. Yeah, sorry about that. Yeah. Okay. So, yeah, so the vertices of the tree in this case are basically lattices in Q2 square in the Q2 plane. And yeah, so the action is the way that SL2Q moves these lattices, because lattices are defined by pair of numbers in Q2P. They're linear independent basis. And then that's the way SL2QP acts. And there is also a relation, containment. If you want to have an arrow from one vertex to another, there's a containment of lattices. So this gives what you see is basically here is the hyperbolic or ADS anti-de Sitter space uh, over Q2 essentially. This is the boundary and this is the bulk. And so the guy SL2Q2 acts isometrically on this and acts conformally on the boundary. So yeah, I mean, okay, so I don't want to get into that, but they use these analogies to come up with a precise, actually, understanding of this, um, yeah, of this ADS CFT correspondence. I don't think I should go into that, but okay, so just briefly, let me tell you that this TP is really, yeah, it's really like a hyperbolic plane with constant negative curvature -1. Exactly, this is the Poincare upper half plane, and yeah, geodesic, except it's a kind of extreme case of hyperbolic space, metric space, where geodesics, basically, there are no geodesic triangles except tripods. So you see, in the hyperbolic plane, these geodesic triangles are, yeah, this, because the sum of angles is less than pi always in the hyperbolic plane. Here, the sum of angles is extremely less than pi, is zero. So this is an extreme case of hyperbolic plane, but nevertheless, it is a hyperbolic space. There are no loops. Geodesics are unique, and so this property. So,
Sorry, can you say again what this TP was at the very beginning?
oh,
TP.
TP is the analog of Poincare upper half plane.
Okay.
Yeah, this is the quotient of SL2QP by SL2ZP. It's like the analog on the left-hand side. Yeah.
Thank you.
Yeah. Okay. So I don't want to tell you about that now. Okay, I spent so much time telling you why QP is useful. Now I want to tell you why QP is not, or why QP or CP for that matter is not good enough. So the idea is the following. You see, what you really want to do, you want to do a theory of complex analytic spaces over p-adic numbers, basically like complex manifolds, and you want to do analogs of complex manifolds over p-adic numbers, and then you want to do something like Hodge theory in this p-adic world, because we know that complex manifolds are much more beautiful actually than ordinary manifold, they have much more symmetry. Like this Hodge decomposition theorem for cohomology of complex manifolds is much stronger than the usual real manifold, Riemannian manifold, Hodge decomposition. So there's a lot of symmetry in the cohomology of complex manifolds that you don't see in real manifolds. Also, there's a lot of restrictions in the fundamental groups that you don't see in ordinary manifolds. So you want to have this theory, but if you try something like that, immediately it blows up in your face. For example, if you take this function, which is obviously in any reasonable theory, this function f of z, which is constant 1 and 0, it's locally constant, so should be analytic. And if that's the case, then it means that you have violated unique analytic continuation principle, because instead of 0, you can define 2, 3, whatever. There's no maximum principle. It violates maximum principle, and it violates existence of global power series in the sense that if you have an analytic function in the plane, the power series converges everywhere for entire functions. But it cannot be a power series for this one. So this was a big problem already for a long time. So there was several solutions proposed. One, of course, was Tate's rigid analytic geometry, which is very useful and is an important development. So what Tate does, instead of usual topology, he uses Grothendieck topology. So he keeps the point, but he changes the open sets. So he's taking much less open sets. And then they don't form a usual topology, they form Grothendieck topology. But he can define analogs of complex analytic spaces. This is called Tate's rigid analytic geometry. The Schulze, of course, is perfectoid spaces. But then there is Berkovich in 1980, I believe, which is this, I will talk about it, this Berkovich spectrum, which is a proposal to fix this issue. And so basically now the plan is how we can add points to CP to turn it into a really nice space, very nice space, actually. So this is a problem of that Berkovich struggled with and came up with a beautiful solution. And actually, for us in functional analysis, for example, it should be very kind of easy, much easier to understand, because we use a spectrum all the time. So in usual operator algebra, algebraic geometry, points correspond to either maximal ideals or prime ideals, depending if you are in algebra or analysis, C-star algebras, maximal ideals, Barbonic algebras, maximal ideals. In pure algebra, you use prime ideals. You have to. So the idea of Berkovich was the following: to complete a space, a p-adic space or non-Archimedean space, into something good, you replace points not by ideals, but by multiplicative seminorms. So multiplicative seminorms, it's clear what they should be. I mean, they are seminorms, then they are multiplicative, strictly multiplicative. That's it. So, okay, so this is like a Gelfand spectrum in functional analysis. So when you do this to your p-adic spaces, the resulting spaces become uniquely path connected. They become locally compact, which it wasn't before. They become Hausdorff, so okay. But amazingly, they acquire a tree-like structure, and I said tree-like. It's more than a tree. It's really like an R tree. That's what they call R tree. So there is a metric that emerges, and yeah, so it becomes like a one-dimensional space instead of bunch of points in this totally disconnected space. So that's the thing. So now my plan is to explain this for CP. and then see what we can do with that. Okay, so now the definition of this Berkovich spectrum. So if you take a complete non-Archimedean field K and a Banach algebra over K. So, okay, I mean, you can think of K as CP. Just take CP for K and take a Banach algebra over CP, the way you look at Banach algebras, complex Banach algebras, for example. So the Berkovich spectrum of A, which we denote by M of A, is the set of multiplicative seminorms on A. So these are the properties of multiplicative seminorm. The only condition that we have to be a little careful is that the seminorm should be that it actually extends the value of the seminorm, the valuation, the absolute value that you already have on K. So we are assuming, of course, A to be unital. So we are assuming that K embeds in A through this unit. So we want to extend this absolute value that exists on K into a multiplicative seminorm. So that's the Berkovich spectrum. So you can topologize that not by some fancy in a fancy way, in really like the way we do in functional analysis. So let me give you an example. So if you take, for example, K, let K to be CP, or just this non-Archimedean complete absolute value field K, then we take this algebra K of T, then the Berkovich line, affine line over K, is this Berkovich spectrum of the polynomial ring with coefficients in K. Yeah, this is the Berkovich affine line. And you can topologize that. This is a set of point. You can topologize that by, you can topologize that by declaring the weakest topology. So this is the topology that all these maps, evaluation maps, are the weakest topology for which all evaluation maps are continuous. That's like exactly like what we do in Gelfand's theory. So now, what are these? So what are some examples here? Of course, every ordinary point A in K defines a seminorm by evaluation. You take the usual f of absolute value of f of A. So this gives you, a seminorm, multiplicative seminorm. But the Berkovich thing is that it allows many more types of seminorms. And in some cases, you can completely characterize what they are. So one thing that plays a big role in this characterization is that disks in the original space actually become points of the Berkovich spectrum. And that's really an important feature here. So let me tell you how it works. So if you consider closed disk in K, you can define a multiplicative seminorm to be a sup of absolute value of f of x for x in this disk. So you evaluate, take the maximum. So this is one type of seminorms. So disks become points of Berkovich space.
Okay, so may I have a question?
Yeah, sure.
So what is special about disk? How about different? Okay, I suppose that it's not possible to define any region since this is a subset of this K, yes? So
yeah.
But how about, for example, union of disks?
Yeah, so union of disks, Yeah, so there is a theorem that basically tells you that what are the possibilities. Maybe if you
Uh-huh.
see the theorem, will give you a little
Okay.
more
Okay.
idea because yeah, you're right. You can think of what about maximum over ellipses, for example, or all kinds of different domains or unions and things like that. Yeah, but let me give you this Berkovich characterization of
Yeah.
all possible multiplicative semi-norms, at least in one example that's very relevant for us. And maybe that will give you some idea. Okay, so there is some questions in the chat, but Piotr, can you check the questions in the chat? See.
I think that it
Well,
was already answered.
all of
Oh,
them were
okay.
answered.
Okay, very good, very good. Yeah, because I was not sure. So the Berkovich classification of points of the affine line is that yeah, they are in 4 types. Yeah, so type 1 are ordinary points of uh, K as we discussed. And type 2, I mean, type 2 and type 3 are not okay. So let me read from what. So these are closed disks as we discussed, but the issue that what distinguishes them is the radius. So in the type 2 case, the radius is actually belongs to the value group of the base field K. And in the type 3 case, which is, we can call it irrational disks, although I don't know. I mean, irrationality is not, maybe it's not the right word, but it's called irrational disks. So these are disks with radius not in the value group, but they're still of disk type. They are disk type. Now, there is this fourth type, which is the following situation. So you can have sequences of disks that actually they're kind of telescoping into each other. They decrease, decrease, decrease. And it could happen that with this, in this p-adic thing, the intersection is empty actually. So they are spherically incomplete, it's called. So, but you want to have, but we don't know this property, for example, I mean, for locally compact spaces. I mean, for R, for example, this is a crucial property that if you have intersections of, yeah, I mean, closed intervals, which are nested closed intervals, the intersection is non-empty. That's an important completeness property. So, but here, but in this p-adic thing, it doesn't. So you add such things. Of course, you can have different sequences, nested sequences, in a suitable sense, defining the same limit point. So you can define this suitable sense. So in the affine case, this is what Berkovich did. I mean, proved.
Sorry?
So
Still
can I
one.
ask?
Sorry.
Yes.
No, I wanted to ask something because it's not completely clear to me. So these points are multiplicative seminorms, not just submultiplicative. But why the supremum norm is multiplicative? So the norm of A times B should be equal to norm of A times norm of B, not just
That's
less equal.
that's no, sorry, norm of A times B should be, should be product of the norms, yeah.
Yeah, but why is this true for the supremum norm? Or maybe it's obvious, it's just
Oh,
not
yeah,
clear to me.
yeah. This, yes, no. That's a very good point. I believe this follows from Gauss' lemma in the theory of polynomials, actually. Yeah. I think this should follow from Gauss' lemma. Yeah.
So is a property of the class of functions, not of
Yes.
the seminar,
Yes.
not of,
We are not. Yeah, exactly. I mean, we are looking at polynomials in this case, and yeah, I mean, yeah, this is also used in the theory of heights, I believe. So I think this follows from Gauss' lemma. Yeah,
okay, thanks.
yeah,
Sorry, one more question, if I could.
yeah.
Could,
So
could you
I will send you a
remind,
reference for that. Sorry. Yeah, so go ahead. Yeah, go ahead.
could you remind me, the space, the spectrum, turns out to be Hausdorff or not?
It is Hausdorff, yeah.
It is Hausdorff. So is this fact that you can consider two different disks with the same center but with different radius, one smaller, one larger, is this inclusion somehow reflected in this
You
topology
see,
space?
you see, but a lot of these things come from the fact that we are working over a over a non-Archimedean field. And
Mhm,
you see, if one disk, if two disks intersect, one is
mhm,
necessarily inside the other.
mhm. But still, okay, you
Yeah.
can consider two different seminorms corresponding to those disks, one
Okay.
contained in another, and is this fact somehow reflected in the topology on the spectrum? On the spectrum,
I believe so. Yeah. I believe so. But
since usually, if you have a setting like in algebraic geometry that
mhm.
you consider some things as thought as a points, then if you could consider inclusion between these points, typically this topology wouldn't be Hausdorff, even wouldn't satisfy the T1 axiom that points are
Oh
closed.
yeah.
But
Yeah,
here
yeah, yeah.
everything is Hausdorff, so I'm a little
Yeah.
puzzled by it that you have such a rich structure which somehow is enough to encode different relations between these seminars, but still the underlying space is Hausdorff. So
Yeah, the space is definitely Hausdorff. Yeah, there's definitely Hausdorff. Yeah,
okay.
yeah, it's definitely Hausdorff. Yes, yes. I mean, yeah. I mean, this is one of the features. It's not like Zariski topology, which is not Hausdorff. Yeah, yeah, yeah. Right. I will give you a reference actually soon so that you can see you can read a lot about this. Okay. Yeah, here I say it's Hausdorff now. A lot of problems have been solved by this. So A1, the affine Berkovich line on CP is Hausdorff locally compact. So you can take its 1-point compactification for any locally compact space, 1-point compactification. You get a compact space. This is the Berkovich projective line. You just add the point at infinity. So the properties of this is that Berkovich projective line is uniquely path connected, namely to any 2 points there exists a unique path. And yeah, for any 2 points C and eta of these multiplicative seminorms, there exists a unique embedded path which we denote C and eta joining C to eta. So it's now you can see, you can imagine this in the form of a tree, but a tree that has a metric. It's an R tree, compact tree like a continuum. Yeah. So yeah, so this is kind of thing that we want to work with. There is one point that plays an important role. That's Gauss seminorm, and indeed that's a disk of unit radius around 0. So that's C01. Yeah, I don't know why it's called Gauss point, because maybe it's Gauss lemma is used in order to, as we were discussing, to show that this is actually multiplicative. I believe so. But one, yeah. Now, closed balls define seminorms, and containment of balls gives an order relation. So this CAR is a point which corresponds to a disk of center A, radius R, and similar for BS, if the corresponding balls are contained into each other. So it means that this tree that you get is actually directed. Yeah. Okay, so I tried again to draw using AI some features of this Berkovich affine line or Berkovich um, projective line. Because there's a picture in the literature which everybody is using it. It's really quite scary to look at. So I didn't want to use that. I tried to make something new. It's Yeah, I think Damien thinks it's good, but still is not perfect, but he thinks it's good, so I believe it should be okay. Um, yeah, so I think I can maybe move on instead of focusing on this. So, so what is an R3? So now let's define R3 is a metric space, which is exactly like the way I defined. The examples are Berkovich line, or yeah, is an R3. So R3 is kind of confusing term, but it's really one should not think of them as trees. They're much more than trees because trees are just a combinatorial object. They are like I mean, it's graph like just vertices and edges. There's no metric in it, but here there is a metric. Um, Yeah, so Berkovich spaces behave much more like ordinary geometric space. So now this divide, basically, because of Berkovich work, the divide between p-adic and um, between non-Archimedean and Archimedean is kind of breached. And that's one of the dreams of everybody who is working this to kind of bridge between to create a smooth path between finite places and infinite places. So they should not be so different from each other. And here is one instance that this can be done. So they are uniquely path connected. They are Gromov hyperbolic, locally compact, and Hausdorff again. So these properties been used. So yeah, I mean, if you do like potential theory on the unit disk in the complex plane, there is a lot of beautiful theory there. The theory of green functions, boundary value problems, lot of beautiful stuff that is related to complex analysis in the unit disk. Yeah, and a lot of it actually has been generalized by Baker, by Matthew Baker, Matt Baker, and Romley in this book, Potential Theory and Dynamics on the Berkovich Projective Line. You can read a lot about the kind of hard analysis, analogs of complex analysis they do over these spaces. So what we are doing so we did two things with this. We defined two C-star algebras, actually, and a spectral triple on one of them. So we were mostly interested in defining Dirac operators because Dirac is much more interesting than Laplacian. Of course, Dirac is kind of generator of K homology. Yeah, I mean, there's much deeper geometry and analysis going with Dirac compared to Laplacian. So we wanted to do Dirac theory, and that's spectral triples is the only way to go with that. But then there is another thing which I won't discuss. It's in the paper, another C-star algebra, which is noncommutative C-star algebra. It's more like a graph. It's like a Kunz-Krieger C-star algebras defined through some shift operators, and yeah, it takes a lot of time to explain that. So I mean, certainly, I focus only on one aspect on this Patterson-Sullivan theory, which I still have. I believe. How much time I have, Piotr, by the
You
way?
have at the moment 27 minutes.
27 minutes. Perfect. So in the remaining 27 minutes, I will try to get to Patterson-Sullivan theory in this context. But then there is, as I said, there is this non-commutative C-star algebra aspects, which is also beautiful, I think, and it could connect actually to more mainstream C-star algebra theory because it's analog of Kunz-Krieger, and I hope Damien can talk sometime on that. So yeah, okay. So I will be talking about this Berkovich projective line. So there is this so-called, there are two metrics. One metric is only partially defined. This small metric, we define it like this. The distance between 2 points, which are, you should think of semi-norms, multiplicative semi-norms, or because we are in the case of Berkovich spaces, in the case of a projective line or affine line, they are basically disks. So this distance is defined to be twice diameter of the Xi wedge Xi prime, where Xi wedge Xi prime is the smallest Berkovich disk containing both Xi and Xi prime, minus diameter of Xi minus diameter of Xi prime. So this sort of metrics, the root of these metrics, I believe, is in Gromov's work on this Gromov hyperbolic spaces. So it comes from there. Okay, so this is one thing we use. And there is a part of Berkovich line which can be called Berkovich, the hyperbolic part, which is the full projective line, and you take away the boundaries, which are this projective line over CP. On this hyperbolic part, you can define a different metric to be a rho of x and y, the distance between 2 points. Again, these are two multiplicative seminorms by log of those expressions that we had before. So if you look at the unit disks, there are different metrics in the unit disk. Of course, there is usual Euclidean metric, which is totally useless. But then there is this hyperbolic metric, which is, for example, if you take Klein's model, there is a formula for the hyperbolic distance between 2 points in the unit disk. And so this corresponds to that. This is really the analog of hyperbolic metric. Now, the action of so PGL to CP basically acts isometrically with respect to this metric, exactly the way that you have this Mobius transformations acting isometrically for the Klein disk or Poincare upper half plane in the other case. Okay, so after this, now it's time to define some spectral triples. So we define the spectral triples, and the observation is that this Berkovich line is projective line is the inverse limit of some finite R3s. If you look at that picture, there is a inverse system of trees, and we can use that inverse system of trees to define a directed system of spectral triples. A directed system of spectral triples. And there is a theory of direct limits of spectral triples, which under some suitable conditions, again, gives you a nice spectral triple in the sense that the resulting Dirac operator does again have compact resolvent and has some nice properties. And so we use that theory in this case. So basically, this the algebra is the algebra of Lipschitz, almost C1 functions on this finite R3 for each finite R3 gamma. And Hilbert space is direct sums of Hilbert spaces that we attach to each vertex of the R3. So what is the Hilbert space of the vertex? So basically, because we are going to use some sort of spin, I mean Pauli spinors to define the Dirac. We are going to define an even spectral triple. This is c to the power twice n nu, n or nv, I should say, is the number of so what's it called? It's called the degree of that vertex. So there's a number of edges that comes to that vertex.
Sorry, just a stupid question. This HV is finite dimensional. Is it true?
HV, yes, it is finite.
Okay, but after all, you are taking inverse limits, so the final spectral triple would be infinite dimensional. Yes?
Oh yeah.
Okay.
It would be
Great. Thank you.
would be infinite dimensional. So this notation, I don't know, we called it L2 of V, but it's really like, it's a direct sum of many copies of complex numbers indexed by. And so it's a kind of iteration. So what's it called? Inflation of this C2 and Vs. Similar.
Sorry, could you please unravel what you mean by functions on gamma? Gamma is a tree, so I have vertices.
No, gamma is an R tree. So it's an R tree. So you see, think of it as, for example, each piece think of it as some interval.
So so you mean points on these trees?
Yeah.
I've got you.
Okay, thanks. Right. I mean, that's so it's a bit like the theory of quantum graphs, but not in your sense, quantum graphs. I mean, in the sense of people who are doing, quantum graph theory.
This is a kind of tautological explanation.
Okay. Yeah, that's the other group's quantum graphs, anyhow. So yeah, it's very much like that. Yeah. And the Dirac operator is basically we are using I mean this so this what's it called? The distance between vertices basically comes into the definition of the Dirac operator as 1 over the distance. Yeah, so this is like Alain's always emphasized that this Dirac operator is the what's it called? Is the propagator, which means is a green function, or in this case it's x minus y inverse. So it comes into that. Sigma x is Pauli spin matrix sigma x, which is 0, 1, 1, off diagonal 1, 1. Yeah. So, so this sort of Dirac operator, we did not check it. That's actually something should be checked. It's quite possible that this is actually really the square root of the Laplacian Matt Baker and Romley took in their work in their papers. That Laplacian is just a graph Laplacian. That's a graph Laplacian. But I don't know. That's a good thing to investigate if the gamma squared is really like Laplacian gamma. If there may be some curvature terms, I don't know, but that's something that comes into. So we have that.
Sorry, but I'm a little bit puzzled since you have those distances. You don't work with plane graph, but with something like an R tree. So,
it is, we are working with R trees. Yeah.
Yes, but this graph Laplacian is purely combinatorial, yes?
Yeah, but you can, you see, in their theory, you can also consider the case where edges have lengths. So these are in electric network theory, they're called, I think the distance is inverse of resistance. So you can attach resistance to each edge, and then you can modify your Laplacian accordingly. And that's more or less what we're doing here.
I see. Oh, okay. So there is also like an R3 version of this graph Laplacian, yes?
Yes. There is something, yeah.
Okay, thank you.
Although, I think one has to be careful about, okay. So I don't want to say more because I don't have a good understanding right now myself. Yeah. But but that part certainly can be done.
Okay, thank you.
Yeah. So we have that. So then you play the game as I said. So you have these inverse systems of these retraction maps from bigger R3 to smaller R3, and gives you a morphism of spectral triples. You get direct system of spectral triples, and you can take the limit. There are some conditions that under what conditions direct limits of a spectral triples defines again a spectral triple. And in this case, you do get a spectral triple. Okay, I mean, you get a spectral triple which is commutative because the algebra is commutative, but the Dirac operator is quite interesting. Yeah. So this is, I just recalled what I said. So there's not much more to discuss here. So here also, I mean, it's a notation. It's just a term notation that I established. The notation here, there's not, as I said, one should really compare the square of D with the Laplacian studied by Baker and Romley in their book. Now, we want to get into one of the things we did, as I said, is this Patterson-Sullivan theory. So I thought, again, I made this to explain things. I think this picture explains it much better than words in this case. So this has to do with kind of, how to say this, Fuchsian, for example, uniformization of Riemann surfaces. So you have this, Poincare disk, if you want, or you can work also with upper half plane, but that's Poincare disk H2 is perhaps more convenient. And then but by uniformization theorem, we know that any compact Riemann surface is actually a quotient of genus bigger than or equal to 2, because genus 0 and genus 1 are kind of special and they are much easier to understand compared to higher genus. Any compact Riemann surface is really a quotient of this disk, Poincare disk or Klein disk, by a discrete Fuchsian subgroup of PSL2R. So you fix one of these things, and then you study the limit sets of this action. So the limit set is you look at the point and you look at the orbit of the point as you go to, as you look at the orbit of the point, and then you define a kind of equivalence relation among different orbits, and then these different orbits define this limit set lambda gamma. And this limit set lambda gamma is a very exotic object, and it captures a lot of dynamics of these group actions. And so one of the things you want to do, you want, which was done by Patterson first, is to define a measure on these boundary points, which is actually supported on the limit set. And it's kind of showing the density of the orbits as they approach to the boundary. So it basically measures a probability measure on the boundary, which measures the density of orbits. And the way that it was defined by Patterson first is quite interesting. Maybe instead of using this picture, I think I will have actually, yeah, okay, so I have the expression, that's better. So there is a classic object in all of this theory. This is Poincaré's series, because in Poincaré's work, when he wanted to generalize all of the theory of theta functions and automorphic functions from genus 1 to higher genus, he came up with such series. If you want, it's, I don't know, it's kind of averaging over the action of the group, discrete group that defines the Riemann surface. So Poincaré's idea was to take this sort of series and take their quotients, and they would define meromorphic functions on higher genus Riemann surfaces. And they basically describe the algebra meromorphic functions describe the Riemann higher genus Riemann surface the way that theta functions, for example, describe different elliptic curves. So this is a very highly interesting generalization of theory of theta functions that Poincaré came up with. But in the work of Patterson, so you put that index S over there, and then basically you can show that this converges for large S and diverge for a small s, and at the critical point there is this number delta gamma, the critical exponent is defined. Of course, I mean, looking at the series, you can see that immediately you can define this delta gamma as lim sup of 1 over r log of number of points in the orbit that's inside the disk of radius r. So this shows how fast these points grow, number of these points grow. Yeah, so delta gamma is the exponential growth rate of the orbit. Now, the importance of, so this whole thing, if you look at, I mean, this sort of statistical mechanics, these expressions come very much from also statistical mechanics. They are like Gibbs measures and in ensemble theory. So, yeah, so it's not surprising that you use this to define a probability measure on the boundary thing, but so this is kind of thermodynamic limit. This is more or less what we were discussing. So this as S, the inverse temperature, S approaches delta gamma, this basically Patterson showed that this approaches a probability measure on the boundary. So this is quite a delicate limit, which is supported. The probability measure is supported on the limit set lambda gamma inside the boundary, and what happens is that the Hausdorff dimension of the limit set is exactly this delta gamma number, and then Sullivan extended all of this using this using what I will describe more or less. I won't describe Sullivan's approach completely, but I will just say some words about Sullivan's generalization. So, yeah, Sullivan's generalization of that is based on something we call Boozman co-cycle. You see, the reason I'm talking about these things is that all of these things we noticed actually can be extended to this Berkovich setting. I'm not sure it can be extended to like p-adic settings because you don't have any of these tools. So John Lott actually studied these things from the point of view that I'm discussing already in his papers. So gosh, many years ago, 10, 15, maybe 20 years ago, he wrote some papers about these boundary actions, cross-product algebras, and a lot of these things. So that was quite a revelation for us. So yeah, so but Lott was in so he took this this Patterson-Sullivan theory and put it in this non-commutative context of cross-product algebras, KMS states, and this thing. So we'll see how this actually carries over to this Berkovich setting. So yeah, this Boozman co-cycle, which is defined again by this sort of delicate limit, it's kind of hard even to show that the limit exists. They essentially measure radon-Nikodym derivatives of different, the different measures that was constructed by Sullivan, d mu x, d mu y, for different points x and y on the boundary. You define these measures, and this is more or less, log of the radon-Nikodym derivative. They have gamma equivariance property, and as I said, they detect host of dimension. So orbit growth, boundary geometry, host of dimension, they all come into one package in this approach. So now the goal now again is to use this spectral triple to come up with a cross-product algebra with an action cross-product algebra, and then show the correspondence between KMS states and on this cross-product algebra and this thing. So so we are now back to our p-adic setting. So boundary of the Berkovich line is, I said several times already, is the projective line over CP. So you take a p-adic Schottky group gamma inside PGL2CP, and so again, I should say this Schottky groups, p-adic Schottky groups, and there's a kind of uniformization of Riemann surfaces over p-adic numbers due to Mumford using Schottky groups. And this was used by Marcoli and Konzani, again, some 10, 15 years ago. There are like some beautiful papers they published back then. And they looked at Mumford curves, and they defined some spectral triples over Mumford curves on that case. So that paper also was very important for us. So I mean, of course, I mean, this is not like they are not like in the Berkovich setting, but the philosophy is similar. So we define a one-parameter group of automorphisms of this because you have the action of gamma on P1 of C, you have the C star reduced on that, and then one-parameter group of automorphisms using this Boozman co-cycle. So this Boozman co-cycle, when they are based on Gauss point, there is a there's a rather different looking definition in terms of log of the quotient of diameters of the orbit points and the base point. And so this is now, okay, now you see this is a one parameter group of automorphisms. And what we need is what we need is so maybe I just say so here I think there's a little bit off the place here, I'm afraid. So this should be a little bit earlier explained. I should have explained. This is here I try to explain Sullivan's construction. So instead of conformal maps, so they are you look at quasi-conformal maps. In this case, they satisfy this inequality. And yeah, so this was in the case of the original case over R and C, complex numbers, was Sullivan's case. And then you check that actually similar definitions work in this non-Archimedean case of Berkovich case. So this allows you to define this Boozman co-cycle by this method. Okay, so yeah, and then Poincare series you can define as in the classical case. You prove again similar things happen. So there is a critical point. Below the critical point, divergence. Above the critical point is convergent. And you get these measures, the Patterson-Sullivan measures, mu, PS, C, and you can use these measures to do integration over this p-adic, over this projective CP. So yeah, so you define this kind of trace. Well, it's not a trace. It's really a I don't know what to say. It's a state, or I don't know. It's a functional. You define it. It's like an integration, tau from C star R. Well, this is the group C star algebra, almost like a group C star algebra. But so basically, you're integrating the component of identity over P1 of C, and you get this. So this gives a positive functional on the reduced cross product algebra, and it plays the role of non-commutative integral associated to the boundary dynamics. And so one of the theorems is that we prove is that the dynamical system, which I defined, admits a unique KMS state at inverse temperature beta equal to delta gamma. And this this KMS state is basically given by the following formula. So yeah, I mean, this was this is I think it's nice because we saw the relation between KMS equilibrium states and Patterson-Sullivan measures in this Berkovich context. Now, of course, from here one can go in many directions. But we have to see what should be the next step. We have some ideas. I mean, there are a lot of open problems, but we have to see which one to take. And so that's basically all I wanted to say for now. And I should say, I mean, in general, the relations between non-commutative geometry and number theory, there are a lot of papers you can look, but of course it starts with papers of Kahn and then Kahn-Konzani. And then I also should emphasize Konzani-Marcoli several papers. I just said one, and also Marcoli's lectures on arithmetic non-commutative geometry is very nicely written and very readable, they are insightful. Again, a lot of references. I mean, for example, we are thinking of analog of Boscan's system in our context also. So yeah, this there's a lot to be done. Well, thank you very much for listening, and this is the reference for our paper. So I think I should stop now. Thank you very much. Yeah.
Thank you so much, MASOUD.
Thank
Thank
you.
you.
Thanks.
Okay, any further questions?
Yeah.
Adam, you are flat.
Yes, I'm wondering about the spectral dimension of this spectral triple coming from this Berkovich line. Is it somehow visible that this is really one-dimensional, or maybe some fractal behavior?
Yeah, this is a good question. I don't know really. I hope I hope it is finite dimensional at least. But even that I don't know.
Oh.
Yeah. This is something to be investigated. Yeah.
But would you bet that it would be something like a fractal, or maybe?
Very much. Very much
Okay.
so, yeah. Because when you take the limit, you don't know what's going to happen. Yeah.
Mm-hmm.
It's quite yeah.
Okay, thank you.
Yeah.
Tomek?
Yes, I have a question.
Yes, Tom.
So in this part about this Klein model, you alluded to uniformization theorem.
Yes.
And so my question is, what about Berkovich curves of higher genus?
Yeah. I believe Berkovich has this theory of complex analytic spaces, even rigid
Yeah.
analytic spaces in general. I didn't dare to delve into his papers. They're quite hard. Yeah.
Is there a spectral triple related to such Berkovich curves of higher genus?
Oh, um, yeah. I don't know what would be even the definition, but you can see some definitions. Yeah. Okay. I suppose it should extend, but I really don't want to claim anything because I'm not. You see, yeah, I think what you're saying is that because, like in the case of manifolds, we have this spectral triple, right? Canonical spectral triple of manifold, which captures a lot of information of the manifold. So if we have a good understanding of this Berkovich theory, of like curves in general. Okay, let's look at curves. Then we should have also spectral triples for them as well. But I mean, Berkovich projective line already itself, this book of Baker and Romley is like 600 pages, 500 pages. No, I mean, it's really a lot of hard analysis there. I mean, and also p-adic theory and non-Archimedean theory. So yeah, no. I mean, that definitely that's a very good question. Another thing is, so Marcoli and Konzani used these spectral triples to they wanted to look at Euler factors at infinity, the Euler factors for zeta functions. So I think something similar to that should be also realizable in this Berkovich context, but we haven't pursued that yet. Yeah, because I mean, I highly recommend their papers. They're quite interesting. Yeah, and
I wonder what could be a relation between this spectral triple and the Riemann-Roch theorem for such curves of higher degree.
yeah. I mean, I believe this should be it. I mean, I think because this, yeah, I mean, because the graph Laplacian already is quite strong. It's very geometric. It's really like the analog of Laplacian because it's defined using the mean value property of Laplacians. You average over all neighboring points.
Yeah.
That's what you do. And here, the Dirac is also very similar. You just divide by the distances, you average over these things. And the Pauli matrices also appear. So, yeah, I think certainly Riemann-Roch is definitely, I think it should be within this context. Yeah, it should be doable. Yeah, definitely. I mean, the good thing about this Berkovich is that it has the still, although I mean it's kind of highly esoteric, but it has still the feel of ordinary geometry. It brings back you from this p-adic world into something more geometric in a way. Yeah.
May I ask another question?
For
Is the
sure.
Dirac operator, in this
Yeah.
case, a Fredholm operator in the sense of, I don't know, Dwork maybe?
Fredholm operator?
Yeah.
Uh,
Is in some
it has
sense.
it has compact resolvent.
Mhm. Mhm.
So it is like yeah, at least I mean basic properties of spectral triples. Yeah. You mean index? You mean taking its index?
Yeah. So what is the index, by the way?
Yeah.
What is
Yeah.
the index?
Yeah, I don't know. Yeah.
So Tomasz, maybe your question was about being finitely summable, yes?
This even I don't know. Yeah.
Ah, okay.
Yeah. Yeah, but it would be very interesting to see.
So finite summability is well suited for Hilbert spaces, but in this p-adic case, I don't know.
Well, I mean, already Work's theory, he develops, I mean, Fredholm theory in the p-adic context.
Mhm.
I mean, Fredholm, no, he doesn't define Fredholm operators, but yeah, I mean, but like Fredholm determinants and theory of compact operators, even Fredholm operators, you can find it in Work's. He used all this to prove the theorem. First conjecture, yeah. Yeah, so that's what it is. Yeah.
Fascinating. Thank you.
Yeah. Thank you. Yeah.
Anybody else? Anybody on the Zoom?
Yes, maybe it's Ludwig. Hi, Masoud.
Hello, Ludwig.
Hi, Ludwig.
Just few additional. So yours, it's not it's odd spectral triple. It's not even. There is no grading there.
It's even. It's even a spectral triple.
You have a
There was a
grading.
gamma.
Yeah,
There was a
there's.
gamma.
But there's a 2x2 matrix there. Yeah.
Okay, but in the formula maybe I was not very careful but sigma X is only one Pauli matrix of diagonal 1 1. No.
Yeah.
Correct.
Off diagonal 1 1. Yeah.
Okay, and this was the grading.
Yeah. This is the grading. Yeah.
I see. Okay, and maybe maybe it was not clear. So you had some Lipschitz function some moment, but you don't have some smooth algebra, some smooth axiom for this spectral triple, nothing like that.
You see, because I mean, for the finite parts, for the finite R3s, we are working on intervals really of different lengths, and Lipschitz functions are enough to define the bounded commutators. Yeah.
Okay. Yeah. That's true. That's true. Okay, but the spectral triple doesn't satisfy this smoothness axiom. Commutators with absolute value of the Dirac operator.
No, that's not. No. I mean, you see, the thing is, you cannot define smooth functions everywhere because you at the nodes, there will be problems,
Okay.
no matter what. Yeah. So
Okay.
you have to work with Lipschitz. Yeah.
Very, very nice. Excellent. It's a new territory for Dirac operators. Okay, thanks.
Oh yeah. This is definitely very much. I think I hope a lot of people work on this. Yeah.
Anybody else? No, Richard, Andrzej. Okay, you guys.
Fine, thank you.
All right, so in this case, that's the end of the academic year 2025-2026. So let us MASOUD again for being such a charming terminator of the academic year. Thank you so much.
Well, thank you very much. Yeah, thank you all. Yeah.
Thank you.
And let me stop recording.
Yeah.
Stop recording.